Good evening. Welcome to the Explorers Club. I'm Alex Moore, and here from the 19th century, the yellow of the map room, I'm bringing you this lecture tonight on the second day of Climate Week. I'm a climate and health scientist here in New York City, as well as Harvard and the Climate Change Institute at the University of Maine. The lecture brought to you tonight was postponed from last year due to an accident, which thankfully has been resolved. And we hope in the future to also have a behind the scenes of the technology that you will see today, which was originally proposed a tour by Katie Bossler with a Fjällräven, and we hope to have that in the future. I would like to thank Ann Passer and unparalleled Mutter for tonight's lecture. And I would like to take a minute to tell you about Professor Ed Cook. I've known Professor Ed Cook for 13 years. He's one of the most inspiring and kind people in climate science and in academia in general and research. We met in 2009 with Paul Majewski, the director of the Climate Change Institute, and Michael McCormick at Harvard, and others in the gardens of Dumbarton Oaks in Washington, D.C. at the Initiative for the Science of the Human Past at Harvard. And one of the first attempts to combine all of the data available to figure out if climate makes empires fall. And we wonder if to find out, you'll have to read our article, which took 3 years to publish. Ed has since published incredible new discoveries that allow anyone to study climate through one of the most important and ubiquitous life forms on the planet, trees. Nature's carbon capture technology. You don't need new technology, we just need trees. Edward R. Cook is Ewing Lamont Research Professor at Lamont Doherty Earth Observatory at Columbia University. He was trained at the University of Arizona Laboratory of Tree Ring Research. And with Gordon Jacoby, Ed co-founded the Tree Ring Laboratory at Lamont in 1975, and is currently its director. His research accomplishments have emphasized the development of new statistical methods for processing tree ring data, the development of networks of tree rings chronologies used for the reconstruction of past climate around the world. Tree rings, if you don't know, can tell us not only how old the tree is, but also how long a drought lasted anywhere in the world for the last millennium and more, thanks to Ed's work. This data is crucial today as we see the most severe drought in recorded history hit the southwestern United States, with Lake Mead at its lowest historic levels and the Colorado River shrinking and giving less and less water to the states around its basin. These long-term research activities have resulted in the development of atlases of drought covering North America, Asia, and Europe, which Ed has published and are available in open access to everyone. These are atlases that reach back in time 2,000 years, giving us a phenomenal insight in how climate has changed and how much more extreme man-made climate change is today. Without further delay, I'll let Professor Ed Cook tell you everything trees can tell us and why they're so invaluable for our climate.
Thank you, Alex. I'm going to share my screen now and start the presentation. Let's see now. Okay. Well, it's an honor to give this talk during Climate Week, certainly. And as Alex very nicely introduced me, the topic is tree rings as natural recorders of climatic variability and change. Now, the need is quite apparent for those who are just observant to what's happening around the world with respect to climate variability of the past years and recent decades. Climate is changing, and there is an urgent need to understand its behavior on decadal to millennial timescales. The instrumental climate records are typically too short to provide us the kind of information to tell if what is happening today is truly unusual or part of the long time scale of natural variability back a millennium or more in the past. But how do we know that the recent warming is highly unusual compared to earlier times? Well, we can tell using the science of dendrochronology. Hold on. Just want to see if I could, is there a way to clear the screen? I guess not. Let's see. All right, well, anyway, we can tell using the science of dendrochronology, which is the study of tree rings. And the name dendrochronology derives from ancient Greek dendron, which means tree, chronos, which means time, and logia, which is study of. Now, dendrochronology was established as a modern science in the early part of the 20th century by its founder, Andrew E. Douglas. And he referred to trees as measuring the lapse of time by means of a slow-geared clock, and this being in their annual tree rings. One tree ring width is formed each year, and that's the slow-geared clock that Douglas was talking about. So tree rings as indicators of past climate. Tree rings records provide the most precise and detailed reconstructions of past climate, covering this past several centuries to millennia. They are annually resolved, exactly dated, and can be directly calibrated in terms of the climate variable reconstructed. It could be rainfall, it could be temperature, drought, stream flow. For example, they can also be they can also extend back hundreds or even thousands of years into the past, thus acting as virtual time machines and provide us information about how climate of the past varied for scientific purposes or for cultural interpretation for that matter. The foundational principle of dendrochronology is cross-dating. Each annual ring is dated to its exact calendar year of formation, so there is zero dating uncertainty. This is the gold standard of geochronology. It's quite different from, say, radiocarbon dating, which can be quite important, quite precise, but still has an uncertainty of, for argument's sake, plus or minus 10, 20, or 30 years, depending on how the radiocarbon measurements are made. And other geochronological measures, radiometric measures of dating have similar uncertainties in dating. Dendrochronology does not. And the principle of cross dating is really quite simple. It is just a matter of matching patterns of wide and narrow rings from one sample to another sample. And in so doing, being sure that the patterns match exactly from the outermost ring, for which we would have the exact year of growth, calendar year of growth, back to the beginning of tree growth in each of the trees. So again, cross-dating is the single most important fundamental principle, foundational principle of dendrochronology. Cross-dating also enables the dating of remnant wood from trees that died sometime in the unknown past, and from samples taken from previously undated archaeological structures. And this has revolutionized the understanding of past cultures, when the cultures rose and when they fell, for example, based upon the dating of the archaeological timbers in their structures. By combining living and subfossil or a dead wood material, cross-dating exactly dated the abandonment of the Anasazi pueblos and cliff dwellings in the American Southwest to the 1290s, and in the process discovered the Great Pueblo Drought. A. Douglas published a paper in National Geographic magazine titled "The Secret of the Southwest Solved by Talkative Tree Rings," and this is based upon the identification of a major drought that coincided with the final abandonment of the Anasazis in the Four Corners area of the United States. You can see right here, this is the drought period. We see 1276 to 1297, reconstructed by tree rings, exactly dated. And here's the main area of drought, and it's exactly in the Four Corners area, which is right about here, where Mesa Verde is located, for example. So there's no other method that can provide this kind of information with the precision that tree rings and dendrochronology does. back to climate change. What can tree rings tell us about what is happening now? Is the Earth warming in unusual ways? Here is a reconstruction of Northern Hemisphere May, August, or warm season temperatures that puts the recent warming for that season in a long-term perspective. And you can see the reconstruction fully resolved at interannual timescales is this one right here in black, with the uncertainties associated with those estimates in gray. And then one can apply a digital filter, low-pass filter, to the same series using a 20-year spline, as it were, and provide a bit of an easier to examine time series of temperature variability at 20-year or longer timescales. Either way, it's quite apparent that the past several decades have been extremely unusual in their warmth relative to anything that's happened over the past previous thousand years. And this is really a very, very strong bit of evidence for arguing that, in fact, the warming that we are seeing today around the world is driven substantially, not totally, but substantially by human activities through the emission of greenhouse gases into the atmosphere. And this reconstruction was possible through the development of a network of temperature-sensitive tree ring chronologies, those located in black dots around the Northern Hemisphere in this polar projection. This is, in my opinion, the single best reconstruction of hemispheric scale temperature variability done to date. But it could only be done through the development of these networks of tree ring chronologies. Any one series would only give you a part of the story, but it would not give you the whole story in terms of a hemispheric scale temperature message. Regarding networks, thousands of tree ring chronologies in the International Tree Ring Data Bank, the ITRDB, can be used to reconstruct gridded drought atlases, as Alex mentioned. These include the North American Drought Atlas here, the Mexican Drought Atlas, located down in here, this area, the Old World Drought Atlas, which is Europe and Mediterranean Africa, and primarily, and the Monsoon Asia Drought Atlas you see right here, okay, in monsoonal Asia and India. These were all developed based upon networks of tree ring chronologies that you see here. Not the exact series used, but this is just an example of the kinds of network that has been developed through the immense amount of work and labor done by dendrochronologists around the world in developing long tree ring chronologies from different areas. The International Tree Ring Data Bank, or network, I should say, is based on finding ancient trees to sample, which can require a lot of exploration. And here are some examples from the MADA, the Monsoon Asia Drought Atlas. Here's an example of a juniper growing in northern Pakistan in the Hunza Valley, located way up here. It began growing in 826 AD. Extraordinary. The instrumental climate records from Pakistan typically are you're lucky if you go back to the 1960s. So this is an amazing bit of additional information that one can get from tree rings, these very long tree ring records in Pakistan. Here's an example from Bhutan, a spruce tree, 700 years of age. The eastern Tibetan Plateau in China, in Qinghai province. These trees right here are hundreds of years old, in some cases over 1,000 years old. And this is by most, the site that I get the most enjoyment out of, in a way. In Nepal, this Himalayan hemlock tree is 1,000 years old. But it took us 13 days trekking to get to this tree. The story that goes into getting there is quite amazing in itself, but it just shows how much effort one has to put into locating these ancient trees sometimes. The NADA in particular, the North American Drought Atlas, includes notable medieval megadroughts of magnitude and duration not seen in modern times. And I would argue that this is a very scary discovery, because what it means is that even without greenhouse gas emissions forcing climate, the climate system has the ability to lapse into what I call mega drought mode, particularly in North America. And to this day, we don't understand the details of why that is so. But here are two continental scale mega droughts, one lasting 29 years, one 28 years, located in the 1100s and in the late 1200s. This should be 1200, not 1300, I should say. But as the world continues to warm, and unfortunately it's very likely to continue, we may now be entering into a new era of megadroughts similar to those found in the past. For the Western United States, this is indicated by the 19-year running mean of tree rings reconstructed drought up to 2018. This result was published in 2020 by Park Williams. I was a co-author on it, along with several other very accomplished dendrochronologists. And this just expresses the reconstruction in terms of a 19-year running mean, and that was chosen by Park to take a look at the how many years of drying this have been going on in the West. And at that time, it was about 19 years. So we wanted to see how would this 19-year running mean compare to the past 19-year running means. And you can see that at the end of 2018, in fact, we're at a extremely dry level that's only exceeded by certainly one event in the late 1500s, and marginally by some others going back into the medieval times. So you can see that this modern megadrought, as of 2018, was very, very significant relative to almost all to the past, almost all the way back at 1200 years. Ominously, this drought has continued now into 2018, 2021, I should say. And here's a map from the United States Drought Monitor for September 7, 2021. And you can see the extraordinary drought going on in the western part of the United States. This drought has resulted in reduced Colorado River flow into the critically important Lake Mead Reservoir. You're probably all familiar with that. It provides water for and electricity for Las Vegas, especially important for those who like to gamble. And now they're gambling with climate in a sense. Here's the Colorado River flow at Lee's Ferry, measure Lee's Ferry, just before it goes into Lake Powell and then into Lake Mead. And you can see that the current discharge rate, in particularly 2021, is 2 consecutive years among the lowest in the entire period of record, going back to almost 100 years. Well, actually more than 100 years now. And even in terms of the past roughly 20 years, we see that the general tendency is for below average inflow into, discharge from the Colorado River. So the past 2 years and the 10-year running mean since 2003 have been very bad. So how does this play out at Lake Mead itself? Well, not well. The Lake Mead Reservoir level has dropped since 2000 to a historic low that has not been seen since it began filling back in the 1930s. And so this is the current height of the reservoir level, and here's where it began filling back in the 1930s. This reduction now has resulted in in water level, water amount, has resulted in a 25% reduction in hydropower generation capacity, which is pretty significant. And were it to continue to drop, you can see that it could get to the point where no power would be produced from Lake Powell. I mean, Lake Mead. Here's the minimum level right now. We have a ways to go, but whether or not we get there, ominously whether we get there or not, really depends on how long the current mega drought lasts. Once again, trees can give us a long time perspective in this regard. Here's a reconstruction of Upper Colorado River annual discharge from 1416 to 2015. Recently published or produced by colleagues out at the Laboratory of Treating Research at the University of Arizona. And you can see this, the interannual variability in the reconstruction. And then one that is smooth with a 10-year running mean to emphasize the lower frequency or more persistent variations in the series. Water resources, people like running means, I should say, and that's why this was done this way. Well, the thing that's scary about this reconstruction is that here's the modern times that we're experiencing right now with Lake Mead down to its lowest level in recorded history. And then you go back in time and you see that, gee whiz, you know, there are many periods that look as bad or worse than what we're seeing now. This is not to say that Lake Mead will continue to drop because of the continuing mega drought. But what it does mean is that we ought not to think that it's going to rebound either. It's honestly more likely probably to not rebound that quickly rather than continue to drop. If one wishes to use this reconstruction as any kind of guidepost. If you're a betting person in Las Vegas, I think that's what I would bet on anyway. So if the future is like the past, we could be in trouble. Prolonged low flow periods are not that rare. Now I'm going to switch over to California now. The previous examples were just for the greater Western United States, with an emphasis on the Colorado River Basin. But California, as we know, is in big trouble from both drought, a crisis of water supply, and wildfire. And this is where I think tree rings can really help us understand what is going on now versus what happened in the past, and how much we should be worried about the future. The 2021 drought in California is a truly exceptional hot drought. And this is the thing that really separates this drought and the drought out west, more or less, pretty much, from previous droughts. Climate warming makes droughts far worse for a given amount of rainfall deficit than would if the climate had not warmed. Here's precipitation for California. Winter precipitation. California is a Mediterranean, has a Mediterranean climate, so almost all precipitation comes in the winter months. And here's from 1895 to the present time. Here's what California looks like, and you can see that it's dried a little bit, but there's nothing that's dramatically drier in the delivery of precipitation to California since 1895. But you look at temperature, summer temperature, and this is when droughts are really, that's what really affects droughts, the severity of droughts. You can see this tremendous warming since the 1990s, early 2000s. That is unprecedented in the past roughly 100 years overall. And this drives up evapotranspiration demand, evaporative water loss from reservoirs. It requires increased irrigation for crops, and the water supply system is extremely stressed by this kind of hot drought. And it translates into the estimation of drought in the form of a soil moisture index called the Palmer Drought Severity Index. So even without it being terribly dry, we still can see that we're in a state of, California is in a state of extreme drought. And it's mostly driven by temperature in this particular case. And as a result, we have this is a extreme drought in California, shown in this map here from the U.S. Drought Monitor, that as of September 7, 2021, that almost the entire state is in extreme or exceptional drought, and it's almost all due to temperature. From tree rings, the earlier 2012, 2014 California drought was found to be the most severe drought of the past 1,200 years. It was also driven by reduced precipitation at very high temperatures, as we can see here. With a level of drought similar to what is being experienced now in 2021. Here's the equivalent Drought Monitor map for California for September 2014. And you can see that it's practically the same in magnitude as the, or severity, drought severity, as the 2021 map. Here's the reconstruction of drought in California back to 800. And here's the instrumental overlap period right here. The match is quite good between the instrumental data and the tree ring data over the past 100 years, roughly speaking. And here is 2014 down here. This is what the is indicated in this reconstruction. 2014 stands out to be worse than any other drought back 1,200 years in the past. There are other droughts, of course, that come close, you know, back here in the 1800s and in the 1500s and like that. But even so, the 2014 stands out. The 2021 drought in California really has created a water supply crisis driven by a combination of below average precipitation, very hot temperatures, and critically below average Sierra snowpack that feeds the rivers and reservoirs. Here's a figure that shows for 2021 the snow water content or equivalent for the northern Sierras, the central Sierras, and the southern Sierras. The 2021 is in dark blue. The maximum snow pack year is in red. Blue is the minimum ever recorded, and here's the average, the mean. And you can see that while 2021 was not did not break any records in terms of minimum snowpack or snow water equivalent for the Sierras, it does fall consistently below the average, and down, and in the south it's actually getting close to what the minimum said occurred in the past. Well, how does this translate into water supply? And water supply means how much water flows down rivers into reservoirs. And we have here a series of reservoirs. I'm sorry, a series of not reservoirs, a series of river records, discharge records that indicate what's happened over the past over the past year. All the discharge from these rivers, 2014, 15, and 2021, all show well below average in discharge. In some cases, only down to 25% of the maximum recorded discharge. And this is because of reduced snowpack and the snow melt, and also the fact that the snow is melting earlier and is evaporating away earlier because of higher temperatures. So there's actually less efficiency, runoff efficiency, in the form of meltwater from snowpacks into the rivers. And this all contributes in a very bad way to reductions in water supply. Tree rings can help in this case too, to understand the past. Here's a tree ring reconstruction of snow water equivalent for the Sierras of Northern California. And it also, and the location of this reconstruction is right here in Northern California, on the not far from Reno, Nevada, on the west side of the Sierras crest. And the reconstruction goes back into the 1600s. And here's the modern period right here, snow water equivalent reconstructed by tree rings. And for the most part, it's well below average. You can say that, well, it doesn't look that bad compared to, or as bad compared to the 1920s and 30s here. But remember, again, this was a much cooler period of time. Here, it's very, very hot. So the impact of temperature on this reduced snowpack or snow water equivalent is much bigger than it would have, than the temperature effect would have been on runoff coming from the snow water, the snowpack back in this period right here. So this is another example how tree rings can inform us about the variability of in this particular case, snow water equivalent that feeds into the rivers and reservoirs of California, the Sierra Nevadas. We can then, so we've looked at the snow water equivalent runoff and the effect on runoff. And then we can look at the reservoirs. How are the reservoirs themselves doing? Because if the reservoirs themselves are big enough and they can hold enough water, maybe it doesn't matter so much that the reservoirs are that the runoff into the reservoirs is not as high as it should be. Well, here are the current reservoirs levels as of September 15th, 2021. Blue is the current level. Okay, here is the average, and this would be the maximum. Okay. In every case, except for one, I should say, one oddball one down here, or two of them down here. And in all the cases, they are significant. The reservoirs are significantly below average. And this again is an expression of reduced runoff reaching the reservoirs from melting snow in the Sierras. The poster child for this problem is Lake Oroville. Now, ironically, you might remember back a couple of years ago, Lake Oroville was almost in danger of losing its dam, its spillway, because it was filled to capacity and was ready to overtop the dam. And in that case, it could actually destroy the spillway in the process. So you say to yourself, well, gee whiz, how can it be that all of a sudden it's so below average? Well, that's how rapidly things can change in the Sierras with respect to how much snowpack there is in the mountains, delivered in the mountains from winter storms. And here's an aerial photo of Lake Oroville in 2019. This is pretty much at full capacity. And now here it is in 2021, and you can clearly see the rapid reduction in lake and reservoir level in a very short period of time. And here is just a map. I'm not a map, a photo showing the how low the water level has become, and is getting down to the point where the reservoir is no longer usable for hydropower generation. And that's exactly what happened. Lake Oroville's water level has fallen so far that the water authorities have been forced to shut down the hydroelectric power plant there. This power plant can provide power for 800,000 households at full capacity, and yet it's no longer generating anything. This is green power in a sense. We all like to have non-carbon based energy production. And here's an example of losing 800,000, the capacity for generating up to 800,000 or power for 800,000 homes because of a drought. So this is a fairly significant result that one has to worry about for the future. Here's the low point of Lake Oroville, as you can see. Never has it been that low in the past. Now we're going to move on to California wildfires. This just shows that mule deer are not so dumb after all. There's a couple of them standing in a river trying to avoid this conflagration in the background. There's been a lot of tree mortality due to drought in California, and as a result, a lot of fuel wood to burn. Here are the two maps that show tree mortality from drought and wildfire throughout this area right here. The bright red is just from drought, mortality just from drought. And you can see it's been extensive. And you see the same sort of thing here, drought-related tree mortality in a subsequent year, 2017. This has produced a huge amount of fuel wood for wildfires to feed on. And given the drought that's happening now, the future does not look good for California forests. Here again is the drought for 2021. That is absolutely horrifying to look at. And here's a very recent map of 2021 fires in California. Some of them very big. The Dixie Fire, which has been burning for a long time, has burned over, well, it's probably approaching 1 million acres now in size. And then there's the Caldor Fire, not as big, but it threatened Lake Tahoe, the communities around Lake Tahoe. It's now, I believe, somewhat under control. But these are two of the bigger fires that have happened just from caused by the drought, plus lightning strikes and things like that. But ironically, past wildfires in California were not unusual. And how do we know? Well, exactly dated fire scars from tree rings, of course. Here's a cross section of a sugar pine tree in California, showing a whole series of fire scars dated exactly to the year of formation by dendrochronology. And the fire scars are formed at the base of the tree trunk, but the tree is not, oftentimes is not killed. And this means that the fire was typically a low intensity ground fire. And the cambium is wounded, and subsequent callus growth forms that produces characteristic patterns of growth on the side of the tree by where the scar is. And because this part of the trunk of the tree has been opened up, it makes it far more susceptible to subsequent ground fires. And that's why you get this very, very detailed history of ground fires coming through the area. Here's another example from giant sequoias. It goes back much further in time, worked by Tom Sweat and others at the Tucson Tree Ring Lab. And the link between drought and from the NADA and fire scars is quite obvious, even in terms of the long-term trend of drought, which is in the dashed black line, versus fire frequency in red. You can see the overall trend matches quite well. So even the giant sequoias have been susceptible in the past to fires. But again, they were primarily lower intensity ground fires, not the stand replacing fires, the crown fires that are talked about so much nowadays. Now the giant sequoias are threatened by fire again. It's in the news just recently, over the past few days to a week. The KNP complex fire, as it's called, is shown right here. Here's Sequoia National Park, and here's the fire. And this is a very recent map. So the fire still is not that well contained, and there's a lot of concern that the trees and the giant sequoias will be threatened by an expansion of this fire You can see the fire here and the smoke plume from the KMP complex, and also another fire down here called the Windy Fire. The Windy Fire. Now, there's been some effort to try to protect the giant sequoias, particularly in the big tourist areas. And the largest tree in the world is the General Sherman tree. It's something like 36 feet in diameter. It's just massive. And so effectively what amounts to like a heavy aluminum foil has been wrapped around the base of the tree in an effort to protect from fire. But as I'll show you in the next slide, there's a problem with this thing, because while the fire may not hurt the tree if it just comes along to the base of it, you have this tree right here that's probably 30, 40 feet tall, young tree, that could catch fire and help damage or kill the General Sherman tree by its very presence in creating a much bigger fire around the tree. And it's remarkable that the Park Service has not taken out all these small trees. I think it's almost it's shocking in a way that this hasn't been done, because these trees are a direct danger as well to the General Sherman tree, but through the way that they could catch fire and make the fire far worse. The legacy of 20th century fire suppression has also, let me just point it, go back, oops, I'm sorry. The legacy of 20th century fire suppression has resulted in a great increase in forest ingrowth and a large buildup of fuel wood for over the many years. And you can see the effect of this forest fire suppression in this sugar pine sample right here with all these fire scars. Then the U.S. Forest Service came into being and established a fire suppression policy. And after 1896, there were no more fires up to the time when the tree was cut. It's clearly not natural. Had the fires continued to burn at the frequency seen here, there would not have been any buildup of fuel wood. It wouldn't been much ingrowth, buildup of fuel wood, and a greatly reduced likelihood of these catastrophic stand replacing fires. This photograph right here really shows it quite clearly. Here's a photograph of a cabin in 1915 in Palumas National Forest, California, completely open around it. Here's the same cabin in 2002. It's like in the jungle of forest now, and that's all because the well, at least greatly due to the fire suppression policies of the U.S. Forest Service. That's changed now. The Forest Service has understood that fire suppression cannot be allowed to continue in the way it had in the past. And so there's a lot of effort to try to create these controlled burns that would allow for ingrowth to be removed more or less naturally, and try to reestablish the forest in the old style of growth in which there was not much ingrowth to worry about for creating catastrophic fires. And I'm gonna stop now and take questions, but I'd just like to finish off by saying that dendrochronology has been hugely important in developing a better understanding of climate variability and change over the past millennium. However, its message is as important as its message is. It's somewhat disquieting because it tells us in a way how bad things may be getting in the future. And thus, we still have a lot of work ahead for dealing with future climatic change. And with that, I'll say thank you for your time, and I'd be happy to answer any questions.
Well, thank you so much, Ed, for that outstanding lecture. I'm, as always, astonished by your knowledge and just the breadth of your data and how much it can tell us about what's going on today, and how much learning from the past can really find solutions for the future. I found myself smiling while you were like talking about California, because about a year ago with Paul Majewski and another colleague, Charles Norkey, we published an article on why climate matters. We were around the election, and I created this slide with my students in climate communications class. And it's basically what you just showed in 2 or 3 slides. It's exactly the same thing, right? You have the Central Valley of California, which produces 40% of our fruits and nuts domestically, and 8,600 wildfires. This is from last season, last year. Last year, we were right here at the same time talking about the same thing with fire chief, and you were supposed to follow. And all of this land is irrigated, and there are 250 crops, which are a $17 billion per year economy. And this is artificial. We weren't supposed to be growing food here.
Right.
And now we have not only diverted rivers, but also suppressed fire, as you said, in order to create this artificial environment in this state, which is a wonderful state. And they're populated by wonderful people, but nonetheless, we're reliant on an unsustainable artificial environment that is causing a lot of strife and a lot of problems because of wildfire smoke, if not for nothing else for humans, but water stress, and also, of course, the little covered, it's known, but little covered story of the plight of wildlife, which very few stories are ever dedicated to, because everybody thinks that nature is here to serve us, which of course it isn't. I have some questions from the audience, and they don't come in any particular order, so forgive me if there is no logic in the order. The first question is from Luna Isiao. Forgive me if I pronounce that incorrectly. Regarding relative temperature and ancient time, can you compare the accuracy level of tree ring cross-dating with the method of testing oxygen ratio, isotopes, oxygen isotope ratios of air bubbles inside extracted ice cores in Greenland and Antarctica? Basically, how much more accurate are tree ring is dendrochronological data than compared to oxygen isotopes in understanding temperature, or really what we can tell is precipitation, right?
Right. Well, I think the big question relates to how accurate you can date the ice cores that are the source of the air bubbles that are used to measure the CO2 content of the atmosphere. And I must say that in certain locations, they're as good as tree rings. The layers of ice can be dated to an annual level of resolution. The Law of Dome in Antarctica, for example. I think some of the higher accumulation rates in areas in Greenland too, but there's very few of them that are like that. I would argue that as important as these very, very well dated ice cores are, they represent a very restricted a number in terms of the global coverage, and the trees give us in more temperate latitudes. Of course, it's a different story. We can also measure oxygen isotopes in trees too, and that's increasingly being done over in Europe, for example, and in the U.S. So to extract more climate information from manual tree rings than just based on ring width, for example. But the ice core data is immensely important, and the CO2 measures of the atmosphere from the ice bubble, from the air bubbles in the ice cores, have really told us exactly what the story is with respect to the past variations in CO2 concentration in the atmosphere, and what human activities have done to contribute to the massive increase.
So as somebody who works on isotopes and on ice cores, really, not specifically on isotopes, but I do analyze that data often. Oxygen isotopes, Luna, generally have a decadal resolution at most, even when we have very, very good layer identification, because the isotopes migrate, they diffuse through the ice over time. So really, we would like to have annual, and we would wish that, but we really know that there is diffusion through the ice over time. So decadal versus annual is really, so Ed wins the battle here without doubt.
Okay, I had forgotten about the diffusion argument, but I'm familiar with it now. But you're right. You're right about that. That's right. Yeah, there's all kinds of models account for diffusion.
And I should say, to as a point of personal privilege here, the Cologny-Fetti ice core from the European Alps, which was dug by the Climate Change Institute, University of Maine, in collaboration with the Swiss Institute and the Institute for Science and Impasse at Harvard, funded by Arcadia Fund, as the highest resolution ice core record in existence at the moment. And we do have isotope records, and still we say that nonetheless, mostly decadal.
Okay.
So here's another one. How does the Oregon, Washington, British Columbia region compare to California in terms of, on these issues, which I would imagine means on drought and wildfires? Is Washington, British Columbia worse or better than California?
I would say better than California. In other words, the wildfire hazard is not as great in the, but there are some. But Oregon in particular, I think, has had some serious wildfires this year. Up in British Columbia, one of the biggest problems is there's been a tremendous mortality of trees up there associated with bark beetles. Killing off millions of acres, and that serves as a fuel source for forest fires. So I think there's a problem there too. But and then just this year, the town of Linton in British Columbia hit a temperature of I think it was like 45 degrees Celsius or something like that. And then an all-time record, and then it probably burned down. It was horrible. But the point is that even the Pacific Northwest, which is oftentimes spared the very, very hot temperatures of California and of course the Southwest, have been experiencing unusually warm conditions too. So I'm not sure that Pacific Northwest is necessarily going to be that immune to the problems that we're seeing further south in California, in the future.
So maybe a follow-up to that one from Kim. Is it too late to do controlled fires? Is there a movement to clear small growth trees from lumber mills instead of larger trees, for lumber mills rather than larger trees, in order to get rid of it's really old growth, right? It's fuel that's fallen. It's trees that have fallen that are causing the, right?
Well, not necessarily. The ingrowth, of course, is really what's come in for over the past, let's say, 150 years. It's been, or 120 years, been allowed to come in from due to fire suppression, and they're susceptible to mortality from drought as the old growth. In fact, you might argue that they'd be even more susceptible because the old growth has been there and experienced bad conditions, bad climate conditions in the past, dry conditions like that, and have survived. So they might be in a better position to survive even the current drought. But I think anything that causes mortality in the form of drought-related mortality provides fuel wood for fires, and I think that would affect the younger cohorts of trees as well.
Here's another question about your drought atlases. Stockton Maxwell asks whether it would be possible to bring those atlases to the global south, because so many of the atlases focus on, world drought atlases for Eurasia, and the monsoon atlases for Asia, more in Eastern Asia, and the North American one is mostly about North America. Is there a plan or a possibility to focus on South America, Australia, et cetera?
Well, the answer is it's already been done to a fair degree. It's
Okay.
South America. There's the back in 2020, the South American drought atlas SADA a paper was published by Mariana Morales. I was involved in it, and Ricardo Villalba and others, colleagues from South America, Ricardo Villalba and others were involved in it. And it generated. We produced a drought atlas for the area of South America south of the Amazon basin, because there simply were no tree ring chronologies from the Amazon basin at the time. But the quality of the that drought atlas is there. It's there to be to examine, to work with, and also there's the Australia New Zealand drought atlas that was published several years ago with Jonathan Palmer as the lead author. From so we're trying to. I guess you could say I'm trying to take over the world eventually, but it's you know, can't we needed the tree ring chronologies, and that's where. And that's the stumbling block, as it were, in terms of you know, covering particularly the southern hemisphere. There's far less to work with in parts of the southern hemisphere. In Africa, in particular, very difficult place to work, because the trees there don't necessarily put on annual rings. They can be dated precisely to, you know, the year of formation. But yeah, no, we're working on it. It's happening, but it's happening slowly. I hope I live long enough.
So here's another question about that particular process, which if the club ever does the backstage at the Tree Ring Lab show, it'll be clearer. It's how you sample, right? How you sample these trees, and the question is, must these ancient trees be taken down to get the sample, or can the bore sample be taken as an ice samples? And I know the answer, but I'm going to let you.
Yeah, I know. Well, yeah, we always emphasize the fact that we don't kill the trees except under extraordinary circumstances. We no matter what the trees are we're working with. If they're living trees, we typically only use an increment borer. You know, they call them Swedish increment borers, but they're made in other countries too. That take out long shafts of wood, hopefully to the center of the tree to get the full age of the tree, and it leaves roughly a 5 millimeter hole in the tree. That's all, and the sap and the resins and so on just fill in that hole. And I can tell you that, and my dendrochronology colleagues will agree with it, that I can go back. I've gone back 20 years after coring a tree. It's been tagged, and the tree is still alive. To update, and the tree is still alive, and there's no sign of any sort of meaningful damage to the tree. So no, we really always work to not kill the tree. We, you know, because we want to go back and sample them again in the future.
Okay. There's another question about can shrubs be cross-dated as well as trees?
The answer, they can be, yes. If they have annual rings, shrubs can have annual rings just like trees can. I mean, it's more a question of size. I mean, shrubs tend to be you know, relatively small, maybe multiple stem and like that. But you know, rhododendrons, for example, have been dated. You know, so shrubs, yes, shrubs can be dated without doubt. The big problem with shrubs might be how to sample them, because if you're down really close to the ground where the main stem is located, it's hard to take a core from that location because we got the handle of the borer, you know, hitting the ground. So shrubs are harder to sample, we'll say. But other than that, though, there's no reason why many shrubs cannot be analyzed dendrochronologically for various purposes.
Here's another. Could a high water table cause dendrochronologists to conclude that in a drought, the cross datings actually indicate a heavy period of precipitation?
let me think now. If I understand the question correctly, and I won't say that I completely do, if the water table is high and it is in effect flooding the roots or inhibiting growth due to a saturated soil around where the roots are located, a drought would lower the water table, say, and actually promote growth in that particular case. So there are situations I've seen in the literature that that indicate that droughts in certain very, very wet environments can in fact be beneficial to tree growth. I won't say it's very common, but I think it's certainly possible.
Let's see here. Higher temperatures in California have ecological implications beyond fire. For example, changes in species distribution, forest composition, and carbon sequestration and water cycling. Sounds like Eugene Wall is in the business here.
Yeah, I know Gene very well, as a matter of fact.
Can Dr. Cook comment?
I'm sure. I missed what was the point of the question?
Higher temperatures in California have ecological implications beyond fire. For example, changes in species distribution, forest composition, and carbon sequestration and water cycling. So how basically do these higher temperatures change what trees are around, how much carbon is sequestered, and how water, well, you've mentioned water, so I guess how much carbon is
well, I mean, certainly in the, high temperatures are going to affect species distributions based upon the tolerance of certain tree species to growing season temperatures. Upper tree line, for example, in the Sierras, is there because the trees, it's too cold higher up for the trees to grow to maintain a positive, a net primary productivity. So that's one way that the distribution will change of a given tree species, because in the tree line environment, as the tree line goes up, the trees can, I mean, you'll see a change in the distribution of given species based upon their temperature sensitivity. I'm not sure exactly what Gene's getting at otherwise.
How about we hop to this question, which will have us go back and forth a little, and then we'll have a fun question after that, and then we can call it a day. Can you briefly, this is Carol Devine, or Divine, forgive me if I don't know the pronunciation. Can you briefly tell us differences and similarities between tree ring and ice core research in reference to climate?
Well, I think the biggest difference, I mean, let's start out by assuming that the ice cores can also provide annually resolved layers of ice, independent of whether or not you have diffusion of the signal, but you can at least say date in other words, if you might have a tephra layer from a volcanic eruption in a given layer, that would not necessarily diffuse. That would be pretty much perhaps locked into a given layer of ice for a given year. The ice cores can go back much further in time than trees. We're talking about tens of thousands of years, of course, where trees can't go back that far. But the one thing that trees have that ice cores don't is spatial distribution. All major continents, all continents other than Antarctica, have trees, and some of them may not be datable or used for dendrochronology, but many are, and many are being explored for potential that was not realized in the past. So I think if you want to think in terms of creating atlases, spatial patterns of variability of climate, trees definitely win, because the spatial distribution of trees is so great relative to ice cores. Ice cores are good for other purposes. They multi-proxy. They produce records of temperature, records of CO2, all kinds of things like that. But I think in terms of and of how we can look at patterns of variability over space and time. The trees have definitely have an advantage over ice cores.
I would agree. As someone who spends a lot of time very, very well guided by Paul Majewski and other colleagues of the Climate Change Institute, thinking about where air comes from so we can figure out what the ice core is actually capturing, right? And trees have a spatial distribution that's much more precise, just because I'm very sure the fact that a tree is static. The other thing I would mention is that ice cores generally are melted once they're dug out. Once they're drilled out of the ice, in most cases they're melted. Occasionally there is an archived copy of it, but most of the ice is melted and then it's no longer recoverable. And it's a lot of ice that was recovered in the last 20 years is no longer there, simply because on the glacier itself, because of climate change. We're losing a record of climate change because of climate change.
That's right.
And really the only place that I know that keeps a lot of these records for future, one of the very few places for future analysis, and that does so systematically, is the Climate Change Institute, where we actually have a non-invasive system to analyze the ice that does not melt the ice, but only creates a groove in the ice with a laser.
Right. Yeah.
And that way you can have very precise data, but very few institutions can support the expense of freezing the stuff, the ice, and then having backup systems that cost a lot of money, a lot of energy to keep this ice in there. Like the gold, it's a golden cap that's going to go away if it melts, because there's no more. Right, you're losing time if it melts on the ice. Yeah. Whereas you have these wonderful little 5 millimeter samples that sit there on a shelf. I'm sure you have to keep them humid, but they're there, right? They're there forever, hopefully.
Well, the thing about them, I've been involved in I sampled hemlock trees over almost the entire range of its distribution in eastern North America, eastern US primarily, back in the early 1980s. And since then, I've had them archived at the lab. And now, colleagues of mine from University of Indiana, from Idaho, and like that, Grant Harley and Stockton Maxwell, and they're now wanting to get my cores and actually measure the blue intensity, the blue reflectance from the surface of the core, in order to extract brand new information that we never even thought existed before. And the fact that those, and I was able to package up all, a whole bunch of sites and send them out to Justin Maxwell at Indiana. And this represents an entirely new use of the cores. And that shows the importance of safely archiving in perpetuity, in a sense, these samples, because a lot of the hemlock sites, in fact, no longer exist because of the hemlock woolly adelgid. So this is an example. This is almost like with the ice cores melting, the ice caps melting, and you can't get the ice cores anymore from the same location. Well, now you can't go back to the same tree ring sites anymore because the trees are gone. The trees have been killed by the adelgid. So
there should be an effort in preserving these records, right, forever.
Absolutely, yeah.
Last perhaps question of the night. It's a fun one. Do you have tree ring art or furniture in your home?
Tree ring art well, let me just for a second.
There you go.
Yeah. Okay, I'm not going to find it here. The answer is not really. I have some samples that in my lab at work. I have some samples of wood that I have on a shelf and like that, because they're particularly interesting and pretty and that sort of thing. But no. Other than that, I guess I'm too much of a geek scientist. I just think in terms of the scientific content and not the aesthetics necessarily of the samples. and how they might be applied to maybe creation of some sort of artwork.
They are beautiful.
Yeah.
They are beautiful. Thank you so much, Ed. It's such a pleasure to see you, and I hope we'll do this again in person. And you're always welcome at the Explorers Club. And just thank you so much for your time tonight.
Well, I greatly appreciate being being asked to give the talk, and be happy to do it again if there was any interest.
All right.
Okay.
Well, thank you so much, and have a good evening. Good evening to everyone, and tune in back next Monday. Oh, tomorrow, actually, Thursday, no, Wednesday and Thursday for the next 2 days of Climate Week. Sorry, it's been a long week already. It's only and then again Monday for our usual Monday lectures. Have a good evening, everyone.
Okay.